Well, it's recording. Palm the projector. Okay. We'll go from current slide. If it will ever come up. Everything seems to be pretty slow today. Let me make just a couple of announcements first. End of the term activity, they published a final exam schedule. I was talking to the dean this morning. I forgot to ask her about this. I think it's wrong. I think we have class on Monday of finals week, which is April 29th, though they list that's the first day of finals. According to the academic calendar and, academic calendar and the administrative calendar, finals don't start till Tuesday the 30th. So I guess I'll adjust that. Well, for us, it really doesn't matter because we'll be, it's a take-home final anyway. It's just that I'll give it to you on Monday rather than the previous Wednesday because I think that's the last day of class. Now, any of you graduating? I know you are, right? Yes. No, you're not. Oh, good. Okay, I thought there was an issue. Okay. No, it's another guy. Never mind. Okay. Any of you graduating this term? Good. So you have all that next week through Monday to get me your the finals back. Okay. So I'll give them to you on that Monday the 29th, and you have until Monday, whatever, 3rd or not 3rd, 6th of May to get them back. All right. Now another error on here. It says we have to have grades in by 12 noon. This is for us on Monday, May 8th, which Monday is the 6th, so that would be hard to do. But on the next page it says Wednesday, May 8th, so I guess they got that sort of correct. All right. Now, this is not necessarily for you guys, preaching to the choir here, but just wanted everyone to know, so spread it around, and especially so anyone who is listening to this, the last day to withdraw from a class on either full-term classes or second mini-term classes is next Tuesday, the 23rd. So if you know of anyone who is possibly behind, good idea to withdraw before next Tuesday. All right, the rest of it I think I've already announced, though several people in this class were honored at Honors and Awards Day. Congratulations to you. I think I said that before, but just in case any of you weren't here when I said it. Okay. Let's get the slide set up. All right. First, any questions? Anything we've done so far? Okay. We were right down to example 5, which is not given on the slide set. If my memory's right, let me just ran forward and make sure that I'm right. Yeah, it's not. A piecewise defined function, and we're asked to what the problem is at different altitudes. This is on page 286, chapter 4, integration, 4.4, fundamental theorem of calculus. At different altitudes in the Earth's atmosphere, sound travels at different speeds. The speed of sound, s of x, in meters per second, can be modeled by, and the problem takes up the whole board here, piecewise defined function, minus 4x plus 341, and that will be from all altitudes from 0 to 11.5. And this 11.5 is in kilometers, I believe. No, yeah, altitude x in kilometers, okay, which may be an issue, but we'll get to that in a minute. And then it's constant at 295 from 11.5 kilometers up. And do they put, yeah, they put the, doesn't matter where they put the equal sign, but I'm trying to do the same as they do, up to 22 kilometers. Okay. 3/4 x plus 278.5. Okay, and there's Taylor. All right. Oh, one other thing I meant to say when I was making announcements. I feel like a broken record here. And this, one of my best classes of all time, one research paper has been turned in, and you only have 2 weekends left. This coming weekend and the next weekend, if that's when you work on your papers. So please get those done. Test 1, there's still 2 people who haven't turned that in, neither one of which is present here today. Test 2, most of you have turned that in, but several have not. Test 3, 2 people have turned that in. Way to go, you two, but please, the rest of you, be getting it in because we're awfully close to test 4. As soon as we finish this chapter, we'll be in test 4. So, 3/4, okay, I got that done. This is from 22 to 32. Kilometers up. 3 halves x plus 254.5. 3 halves x plus 254.5. And this is from 32 to, 50 kilometers up. And finally, negative 3 halves, is that right? Yeah, negative 3 halves x plus 404.5. And that's from 50 to 80. All right. And past that, we assume there's not enough atmosphere there for sound to move much at all. So the speed of sound depends on the altitude. There is a graph of this in your text. I'm not about to try to graph it for you, but it says what is the average speed of sound over the interval from 0 to 80. Okay, now we did average speed or average value of a function, okay, on the previous page, and that, remember, was 1 over b minus a, which will be 80 minus 0. Okay, that's your b minus a, so that's the 1 over 80 times the integral of this function. However, this is a piecewise defined function, so we're going to have to integrate it according to these intervals, limits of the integration, and add those up and then divide by 80. Okay, so basically it's just doing those. So let's do the first one here, integral from 0 to 11.5. Now, yeah. If any of you are concerned, and I would applaud this, being concerned, about that we've got the speed in meters per second, but the altitudes in kilometers, and you might say, oh, but that's not going to be consistent units. You don't really have to worry about it because we're integrating just, well, let's see, you really do, don't you? Yeah, because your dx is in that. So they claim you don't, okay? And there is a reason for it. That the 1 over 80 is going to wipe out the units, the kilometer units. So you can still do that. So what you're integrating is sort of a ridiculous thing. The speed of sound, dx, but the dx is measured in kilometers. This is meters per second. So you got meters per second, kilometers. But then when you divide by the 180, you wipe out the kilometers. So you don't have to worry about them here. Most of the time in physics, that would be a major concern. But the kilometers aren't really entering the picture. You're going to divide them out. So anyway, let's do this. The integral minus 4x plus 341 dx. Okay. Not a bad integration at all. What would that be? Antiderivative of minus 4x. Negative 2x squared plus 341x. Okay, we'll evaluate that from 0 to 11.5. Okay, and is a bit bizarre on the units, but anyway, what does that give us? Calculator time, folks. I'm not going to do that one in my head. Negative 2 times 11.5 squared. Okay, plus 341 times 11.5. $3,921.5. Okay. Whoa. Second? 3657 is what the book got. Oh, you just did the 341 times that. Okay. And subtract from that. Yeah, okay. So let's get that corrected. Okay. Yeah, subtracting the other from it. 3657. Whoa. All right. Next one's need to set up an integral. Anybody? It's constant, right? So you just do 295 times the difference of those two, which is 10.5, right? 295 times 10.5. What does that give you? I hope I'm right on that. Yep. Shouldn't be that hard to punch in, right? Second? 3097. Exactly. 3097.5. Okay? Now, is there any real reason we need to go through all this? The integrations are going to be almost identical. Well, I guess we ought to do one with a fraction in it since we haven't, just for funsies. So let's do that one. The integral from 22 to 32. Now, again, let me pause here a moment here. It really doesn't matter where the equal sign is, or even if you put the equal sign in, because you're always integrating between these two. So whether it's less than or equal to or less than, doesn't matter. You're integrating in between those two, because at that one point, the integral is 0 anyway, so it doesn't really matter. You're just doing that band. So 22 to 32 of 3/4 x plus 278.5 dx. What would that be? We haven't done one with a fraction, or have we? We may have. What would that be? Anybody? Anybody?
6 would be 6 over 4x squared.
Is that right? What is the... Okay, you got x squared, right? Over... Forget the 3/4 for now. Just the x, that would be x squared over 2 times 3/4 would be 3/8, right? You're dividing by 2, not multiplying, right? Okay. And then the next one would be plus 278.5x, evaluated from 22 to 32. Sure not going to do that in my head. So just punch something in quickly and see what you get. 3 times 32 squared divided by 8 plus 278.5 times 32 minus 3 times 22 squared divided by 8 minus 278.5 times 22. Doable? I mean, somebody. Anyone got it done yet? Anyone doing it? I see a few thumbs are working. Black boxes sure are slow, aren't they? Okay. But a lot faster than doing them by hand. Okay. What you get?
15,000.
Whoa! Did you subtract both of the last two? It's this with 32 in it, 32 in it, minus this with 22 in it, minus this with 22 in it. Did you do both minuses there? 2987.5, that's what the book got, so I hope they're right. 2987.5. All right. Rest of them are going to proceed that kind of a way. Do you feel a need to continue practicing your integration? Maybe practice your evaluation of it, but integration. They keep going this way. You get really big numbers, but they're all in the same ballpark here until you get the last one, which is, whoa, because it's such a wide range from 50 to 80. That's a pretty big area there. That's surprising. Well, the last two are pretty big areas. But anyway, you add all those together and then divide by your, and that gives you 2464.80. Divide that by 80, and you get an average speed of, do y'all need the practice of adding them and dividing? Probably not. Okay, so you would get something on the order of 308 meters per second. Okay, which is not far from what we usually use this at average anyway, even though it's sort of all over the board. The other thing that is really rather bizarre about this problem is that the speed of sound also is dependent on temperature and but also altitude. So I don't know if they've included that in here or not. They must have, I would think so, but it's nothing intuitively obvious here that they would have. But that gives you the average speed of sound in air throughout the range from 0 to 80 kilometers up, which is pretty far up. To me, that was an exercise in persistence, okay, doing all those integrals that are very similarly done, but making sure you can do those. All right. Any questions on those? Do you mind if we move on? All right. No objections heard. We'll go to the second fundamental theorem of calculus. Now, other texts will sometimes call this Fundamental Theorem of Calculus Part 1 and Part 2. In fact, I think every other calculus book I've taught from called them that. This is the first one that I remember calling them first and second. In fact, they didn't even call the first one first. It said the Fundamental Theorem of Calculus and then the second Fundamental Theorem of Calculus. Other books call it Part 1 and Part 2. Earlier you saw that the definite integral of f on an interval a to b was defined using a constant b as the upper limit of integration and x as a variable of integration. That's what we did. They didn't even mention b being the lower limit. However, a slightly different situation may arise in which the variable x is used as the upper limit, not b. Okay? Now that seems a bit bizarre, but remember, if x is used in the limit of integration, you're not integrating with respect to x. You're with respect to t or something else, but not x. The variable x up here means it can't be the variable of integration, the dummy variable, they called it earlier. To avoid the confusion of using x in two different ways, t is temporarily used as the variable of integration. I said t, but it could be anything else. Remember, the definite integral is not a function of the variable of integration. That's just sort of a dummy variable there that you're going to evaluate away. So you don't use x both as the limit and as the variable of integration. Just don't do that, okay? So here's what we've got. The definite integral of a number is here's some function that your alpha is a function of x, okay? Alpha of x is a function of x, okay? And you're evaluating between two limits, that gives you a number. That always gives you a number. Now, here, we're doing capital alpha of x, which we have used before as the antiderivative, and indeed, this is sort of what it still is. But this now is a function of x. That's a number. This is a function of x, okay? There's the variable x located there, and your variable of integration could be anything. Stickman, it could be anything, just not x, okay? And you integrate this, whatever variable you want to put in there, and this is a constant, that's your variable, okay? That makes f of x the capital F also a function of x. Little f is now a function of t or whatever variable you want to name, not a function of x. Okay. So, what this gives you is a function that's dependent on an integral, okay? Some places will call it an integral function. But most of the time when they're saying that, they're saying things that can't be solved any other way except as an integral function. This could be, but we're going to get to the reason for making all these changes now. Okay? So here is our function they want us to evaluate at different values for x. Okay? Now, there's one way you could do this, is put these values in and start doing it that way. That's sort of long and arduous. All you do is do this as a function of x and then plug the values in there. That's a little bit easier to do. So let's first do capital F of x. What would that be? Antiderivative of cosine t. Anybody? All right. I think you're taking a derivative of it, aren't you? Antiderivative would be sine t. Why? Because derivative of sine is cosine. If it was a negative sign, that would have been saying the derivative of sine would have been negative cosine, but that's not true. It's sine t. Remember, your signs flip between antiderivatives and derivatives. Okay? Understood? Okay? And now you evaluate that from 0 to x. And what will that be? Sine x. Okay? And if that's your function, then you just plug in these values. At x equals 0, Sine of 0 is, please, if you're in my trig class, you better answer that. No, okay. Sine of 0. Sine of 0. Sine always starts there, right? Sine of 0 is 0, right? Cosine starts up here. You take the value, the x's are going to be your pi values. These are going to be number values, and sine of 0 is 0. Now, let's go back to this one. It better be, because if you're integrating from 0 to 0, that better come out 0, folks. If it doesn't, you've got a really big problem on your hands. And sure enough, it does. Okay? So that indeed is 0. Okay? What's sine of pi 6? Yep. Now that's coming back, isn't it? That's 1/2. Sine of pi 4th? Square root of 2 over 2. Pi 3rds? Square root of 3 over 2. And pi halves? 1. Very good. Okay? Now, thank you for using our favorite values here. Okay. Okay. Now, these are the ones we know and love, right? The pi 6, which is 30 degrees, 45 degrees, 60 degrees, and 90 degrees. We know those values. That we use them over and over again. One easy way to remember them for sine is it's the square root of 0 over 2, the square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, and square root of 4 over 2, which is 2 over 2, which is 1. Okay? So if you have trouble remembering those, if you get them in the right order and have them, that's one pretty easy way to do it. Okay? And they gave us exactly those values here. Thank you very much. Okay. Now you could have plugged this in there and gone through, but you would have been doing the same thing, because then you would have been doing sine of pi 6 minus sine of 0. Sine of 0 is 0, so every one of those would have been the same answer. It better be. Okay? And you might ask yourself, why are we doing this? Okay, but anyway, we won't ask ourselves that. The reason is going to come up. Let's see what they did. You could evaluate 5 different definite integrals, one for each given upper limits, like I said. Any of you really hankering to do that? I hope not, but you could if you wanted to. Ayana is here. Did I say it right that time?
Yes.
Oh my goodness, it must be near the end of the term. Okay. All right. All right. But it's much easier to do the function and then just plug them in. However, it's much simpler to fix x as a constant temporarily to obtain the antiderivative of cosine is sine, and then you evaluate from 0 to x. That gives you sine of x minus sine of 0, but sine of 0 is 0, okay? So that's just sine x. And then you just plug the values in. And what you're measuring then, here is cosine x from 0 to pi halves, and that's as far as we took it, right? All right, so you first measure from 0 to pi 6, and that gave you 1/2. From 0 to pi quarters, that gave you root 2 over 2, a little bit bigger area, and then 0 to pi thirds, much bigger area, and 0 to pi gave you exactly 1. Now, you may run into this in the future, and if you do, don't be surprised, but if the integral of cosine x from 0 to pi halves is 1, that's, remember, sine x is the same shape, same everything, and basically that would be this integral here. Guess what this integral would be? Another 1. Okay? So the integral, if you ever need this again, from 0 to pi of sine x, dx, that's equal to 2. You can do the math, it works, everything plans out, and it's always 2. The area under one loop of a sine curve, or a full loop of a cosine curve, is 2. If you're going 0 to pi, no expansion in that. Just one of those little freaky things of nature, I guess. That's equal to 2. But that wasn't what we're doing here. All right, but in case you ever do it. Now you can think of, and here's the problem, you can think of this function f of x as the accumulating the area under the curve of this as you go from 0 to x. And that's exactly what we saw we're doing the area of a little bit bigger strip every time. For x equals 0, of course, the area is 0, okay, because it's a single line. And f of 0 was 0. For pi halves, it's 1 is the accumulative area under the cosine curve on the interval from 0 to pi halves. That interpretation of an integral as an accumulation function is used often in applications of integration. Okay? If you ever have to do any probability, that's exactly what you're doing in probability. You're doing the area under the probability curve, your probability distribution function, okay? If it's a nice normal curve, you know, then what you're measuring is the area under that curve. That's an accumulation function. Because if you've ever messed with that function, it's not integrable, okay? But it's, you can do it numerically or other ways like that, but that's exactly what probability is doing for you. In example 6, which is the one we just did, note that the derivative of capital F is the original integrand. If you took the derivative of f, remember we used to call f the antiderivative, it still is. Okay? The only difference is the variable has been changed. So d by dx of f of x, that remember was sine x, that was what we got there, and derivative of sine x was cosine x. Well, that's the derivative of this integral. Oh, but look at that. Okay? This result for this function, but it'll work for every function, is generalized in the following theorem called the second fundamental theorem of calculus, which we've sort of already been assuming or saying, but now we get to say it with authority, I guess, is that if you're taking the integral of something, you're doing the antiderivative. Well, if you take the derivative of an integral, okay, then you get back, these are indeed inverse functions of each other. You integrate, you take the derivative, you integrate a function, you're doing the antiderivative of that, sort of the inverse of that. And if you take the derivative of that, you get back to what was on the inside. Okay? That's the second fundamental theorem of calculus. If f is continuous on an open interval I, continuous now, no gaps, no breaks, containing some variable, some constant a, then for every x on the interval, d by dx of the integral from a to x of f of t dt is your f of x. You just plug it in. It's the same function, but evaluated at x. Okay? Now, if you're integrating a perfect derivative, that also almost works out the same way. Okay? We'll see that maybe a little bit later. Using the area model for definite integrals, the approximation of f of x delta x, that's approximately your integral from x to x plus delta x of f of t dt. Now, that seems like we jumped a big rabbit right there suddenly to go to this thing, but that's, is just sort of giving us a differential form of doing what we just said. This can be viewed as saying that the area of the rectangle of height f of x, of a rectangle of height f of x and width delta x is approximately equal to the area of the region lying between the graph of f of x and the x-axis on the interval from x to x with delta x. Okay? So basically what it's saying is here's your x, and there's your f of x. This part here is just saying this is the area of this little rectangle. This, of course, would be the area between x and x plus delta x of the entire function f. So you see, it's not the same, but it's approximately. In some cases, depending on how big your delta x is, the smaller the delta x, the better the approximation, of course. Okay. So, can't figure out exactly why they brought all that up now, but it's certainly a legitimate thing to say. Haven't turned my pages to, yeah, this is the bottom of page 288. Okay? Now, before we do the example 7, it says, note that the second fundamental theorem of calculus, or fundamental calculus theorem of calculus part 2, tells you that when a function is continuous, you can be sure that it has an antiderivative. Okay? The antiderivative need not, however, be an elementary function. In other words, one that we can actually calculate. Okay? So you can, it says section P3, I think that was a preliminary chapter in the book we didn't do. So if you want to go back and look at that, you can. All right. So let's do example 7. Let's evaluate that. The derivative of d by dx of the integral of from 0 to x of square root of t squared plus 1. Anyone want to hazard a guess what that answer might be? The square root of? Not t anymore. X squared plus 1. Okay? Now, that's the derivative of that function. Okay? Right now, we don't have the tools to evaluate what that function is, because we could get there, but not with the tools we have in our tool belt now to even evaluate that function. So you might say that's not an elementary function, but you do know what its derivative is. Okay? That's all there is to it, I can't, at this point, integrate that, but I can take its derivative. Okay. So let's see what they say about it. I don't think I need to erase. Note that f of t is equal to square root of t squared plus 1. Continuous on the entire real number line. Okay. Even negative, even though you got a square root here, because when you square a negative number, you get a non-negative number, add 1 to it, it's always going to be positive, so you can evaluate anywhere over the real number line, so that's even going for negative x's or positive x's. It works. Okay? So using second fundamental theorem of calculus, the integral of that is merely replace dummy variable here with the variable of integration. That's it. That's all there is to it. Okay. Second fundamental theorem of calculus. All right. Now, can they make it more complicated? Of course they can. Give them a chance. Okay? Oh, but we're not doing it. So we're going to have to go back and do example 8. They do the easy ones for you on the slide set. The harder ones, yeah, you have to work on your own. find the derivative of f of x, capital F of x, where that is equal to the integral from pi halves to x squared of cosine t dt. All right. It'll come back, I think. Okay. They want the derivative of f of x, which will be, they write it a couple of ways there, derivative of f of x. That's what they're asking for. And this is d by dx of f of x. Well, wait. Sorry. Here's they snuck it. This is what changes this one. Okay. D by du of du dx. Okay. Now, where does that come from? Well, what we have here is not our second fundamental theorem of calculus. Oh, that's not an x there. That's an x squared. So what they're doing is to use it as a second fundamental, we're going to have to say let u equal x squared. Right? Now, your f prime then of x, okay, if you rewrite this, that would then be the integral from pi halves to u of cosine t dt. See, that's why they changed it there. This is a fundamental theorem of calculus. Problem. We can do that. That will give you, if you take the derivative of that. Okay? But the thing is, by introducing this, you can't take the, okay, this is saying, what they're asking for is derivative of this with respect to x, but you can't do it with respect to x here until you see how they do it. We're going to make the change here, but in making the change, then you have to do the derivative with respect to u times the derivative of u with respect to x. Well, you can do that. What's the derivative of u with respect to x? Anybody? Not that hard. 2x. Okay, very good. So this is going to be this thing right here is what you have down here, cosine t. Okay? Have I I wrote the problem down wrong, didn't I? Sorry about that. My eyes aren't good. I've been noticing this more and more lately, so I went to the eye doctor. Got to have a cataract removed. Okay. So sorry about that. That was an x cubed. I was going to say, how in the world are they getting the answer they got? That's an x cubed. That's an x cubed. Du dx would then be 3x squared. Okay. All right. So, now we can proceed. Okay. And, okay. I've got this a little screwed up here. Let's do this integral first. Okay. Not using fundamental theorem of calculus, part 2. Let's just do the integral. What's the antiderivative of cosine t? Sine t, we remember that, don't we? Sine t evaluated from pi halves to x cubed. And what would that be? Sine of x cubed minus 1. Sine of pi halves is 1. Okay? Now, that is your f of x. What we want is the derivative of f of x, okay? Okay? And derivative of this thing, d by dx, of this thing would be what? Okay? That's an ugly x, isn't it? What would that be? Derivative of sine of x cubed. Ooh, long time back. Derivative of sine. Cosine of x cubed. Then you have to do a, yeah, times the 2x squared. All right. Now, so that's the derivative. So this should be our answer, what it was asking for. Okay. I'm sorry, 3x squared. Again, that was not my eyes, that was just stupidity. Okay. All right, let me get that looking a little better. 3x squared. Okay. Now, and you see the minus 1 no longer in the picture anymore. Okay? Because you see, whatever this evaluates as, it's going to be a constant. And when you take the derivative of that, it disappears. So that's why, if it bothered you that sometimes it was 0, sometimes it was pi half, so it doesn't really matter what it is. It could be an a, and as long as that a is a constant, that just gives you a constant value, and when you take the derivative of it, it disappears. Okay, so that's the answer here. Let's go back to the way they were doing it here, which is a perfectly good way of doing. I kind of got, okay, so we know that's the answer that way. So let's clear that out. Okay. I knew you knew how to do it that way. Let's show how we do it this way. I'm going to leave the answer down there just for fun. Okay. Now, all right. So your f prime, which is d f du, I forgot to put my f in there, times du dx, that is your f of x, and this is a function of x, remember, okay? So they write this in here as d by du of your f of x, okay? And this is, your f of x is this integral here, pi halves to x cubed cosine t dt, okay? All right, that's your f of x, and then your du dx, which we did up here, is 3x squared. See, it's going to show up again now. Well, okay. Let me erase this equal sign. I put it in the wrong place. Okay. Rather than writing x cubed here, we're going to put u, because u is x cubed. Well, I was going to put u, but it won't erase. Okay? Okay. Okay. And we know exactly what this is. This is, like we said before, this is that. So I didn't have to write it twice. But this is, by the fundamental theorem of calculus, wrong place. This thing right here is cosine u. By the fundamental, but cosine u, 3x squared, but u is cosine. U is x cubed. Okay. Roundabout way to get there, but that's what you have. If you stick this thing in there, that's this. Changing the xu to x cubed, and so you just have that. So if you have something up here that's not x, you still do cosine x cubed, exactly what it would have been, but then you also have it sort of like a chain rule issue. Your chain rule, or exactly what it looks like, times the root of whatever your new variable is. So you can't just plug in an x cubed and leave it. That might be your first intuition. Don't. You have to then almost do like a chain rule. In fact, it's just like a chain rule. In this form, you can apply the chain rule to verify that, and sure enough, that's exactly what you get. Okay. So, poorly done, but there it is. Now let's go to net change theorem. Okay. And can't quite figure out why they make such a big deal about it, but let's see what it says. The fundamental theorem of calculus, the first one, okay, states that if f is continuous on the closed interval from A to B, and f is an antiderivative. Now notice how they say an antiderivative of f on A to B. Then, this is what we just did. Antiderivative of this, evaluated at B, minus evaluated at A. First fundamental theorem of calculus, or the one they call just the fundamental theorem of calculus. But because f prime is equal to f of x, which you see, that statement can be rewritten. Why would you, oh yeah, as put the f prime in here. Okay? See what they're doing now. Okay. So if you're taking an integral of a derivative, a perfect derivative, you just, whatever that's the derivative of, again, before, on the second fundamental theorem, the derivative of an integral is whatever's on the inside. Okay? Now you do the integral of the derivative, do a d by dx here rather than df by dx here. Basically, your dx's go out, you're doing a derivative of f, and that's just evaluating capital F of b minus capital F of a. Where the quantity b of a minus f of b minus f of a represents the net change in f on the interval from A to B. Can it be that simple? Well, yeah, it is. Okay. So that, I don't know why they call it net change theorem, but that's certainly true. So here it is written out in the flesh. Okay? The net change theorem, if f prime is the rate of change of a quantity of f, okay, that's what it is. F prime is the rate of change of your function f. Then the definite integral of f prime from A to B is the total change, or the net change, of f over the interval from A to B. So it's just f of A times f of B. Okay. Whatever quantity that was. Okay. To me, the thing here, the derivative of an integral is what's inside. The integral of the derivative is what's inside. Evaluated between those. Now you see, you don't have the difference there when you do the first one, derivative of an integral. You just have what's inside. Here we have a difference, which is kind of like integration having to have a constant with it. But this is a definite integral. But that's your net change. All right, so here's example 9, and I think we're going to apply, this. A chemical flow, how are we doing on time? Okay, we're fine. Okay. Chemical flows into a storage tank at the rate of 180 plus 3t liters per minute. Okay, where t is the time in minutes. And t is between 0 and 60. Okay? Find the amount of the chemical that flows into the tank during the first 20 minutes. Okay? So that's the rate at which it's flowing for 60 minutes. What is the amount of chemical that flows into the tank during the first 20 minutes? Okay? probably helpful to designate your functions. I find it helpful anyway, things that sort of make sense. Rather than just F, why don't we do the chemical flows into a storage tank at a rate of this, where this is find the amount of the chemical. So I like to go to the question here, amount of chemical, that's what we're looking for. So I like to do let A equal the amount of the chemical. Is that okay with you? Okay? That flows into the tank during the first 20 minutes. Well, it's just going to be the amount of the chemical. What does this thing say here? Chemical flows into at a rate of. Well, this is dA/dt. Anytime you see rate of, think whatever it's talking about is the time rate of change, dA/dt. That's what this is. So the problem says dA/dt is equal to 180 plus 3t. Okay, we know that. Where t is the time in minutes and is allowed to go between 0 and 60. So find the amount of chemical that flows into the tank during the first 20 minutes. Okay, that's certainly within that interval. So we can say amount of chemical that flows into the tank would be the integral from 0 to 20, okay, of the rate, which is 180 plus 3t dt. Okay? Now, you can, yep, and they do. I was want to make sure we're going to do it this way. Okay, you can just integrate this. And what's the antiderivative of 180? 180t plus, and what's the antiderivative of 3t? 3t, yeah, 3 halves, if that's what you said. I can't hear well. Can't see, I can't hear, I'm pretty decrepit. Okay, and this is evaluated between 0 and 20, right? Yeah, okay. Plug and chug, and what do you get? I believe that's 3,600, right? Plus 3 times 20 squared is 400, so that would be 1,200 divided by 2 is another 600. Okay, so that would be 4,200, if my calculation's right, and that would be liters. That's how much would flow into the tank in the first 20 minutes. Oh, good for them. Okay? Now, to me, that felt just like an integration problem, and I didn't really think net change theory at all. Okay? But basically what we did was let's see, if we had done 180, no, that wouldn't have been anywhere close. 3 times, okay. That's how they do it. So I don't really see what you did though is find the amount of chemical. That's what you let your variable be. Okay, 8. That's what we're looking for. And then when they say it comes in at a rate, that's the dA/dt. Okay. Now they make, what did they use in the book? They use C prime, which really makes a lot. Oh, maybe for chemical. I don't know. But they do it the same way. And sure enough, that's the answer. And except for the fact that the amount of chemical that we're looking for is the integral of the derivative, okay, I guess that's why they're saying it. But that's what you wind up with. 4,200 liters. Okay. Now, another way it says to illustrate the net change theorem, examine the velocity of a particle moving along a straight line. Let's see if, wait, let me back up and show you how they do it, which I think is pretty close to the same way. Only difference, they say, let C of t be the amount of chemical in the tank at a time t. Okay, they use C of t rather than A of t. Okay. Then C prime represents the rate at which the chemical flows into the tank, and that's exactly what they give you there. So the integral of your derivative is the integral of 180 plus 2t. Just do the integration. Just like we did, and you got 4,200, just like we did. Because when you plug in 0 at the end, you still get 0. Okay. So the amount of chemical is 4,200 liters. Okay. Another way to illustrate the net change theorem, I'm sure that was an illustration, is to examine the velocity of a particle moving along a straight line, where s of t is the position at any time t. Then its velocity is equal to the first derivative of the displacement. So if you want to know what the integral from A to B is, the v of t, if you already know what s is, and that's how you got your v, then that's fine. You can just do s of v minus s of a. But generally, if this is what you're given, you don't know what s is. That definite integral represents the net change in position or displacement of the particle. And that's a net change, and that even allows for if the particle was backing up sometime, still that would be taken into account, believe it or not, okay? And I think they do that from calculating the total distance traveled by a particle. Then you must consider in the intervals where the velocity is 0 and where the velocity is less than 0 or greater than 0. Because if you're traveling and then you do this, and then you turn back and do this, the net change just tells you from there to there. That's a displacement difference. If you want the total distance traveled, you have to do this distance plus this distance, because you still traveled that distance plus that distance. So then you have to break it into pieces. So if you have the net change theorem, just tells you that's your total displacement from beginning to end, not worrying about whether you backed up or went forward, it just gives it to you. If you want total distance, then you have to take into account whether you're going forward or backward, because a distance is a distance. It's not positive or negative. It's always an absolute value. Okay. So when v of t is equal to 0, the particle moves to the left. When it's greater than 0, it's moving to the right. So to calculate the total distance traveled, you integrate the absolute value of this thing, which is can be a pain in the neck. But that's just a piecewise defined function. Just have to be careful that you define it properly. So the displacement of the particle is given simply by this. Okay? Don't worry. Oh, I'm sorry. With this illustration, here the velocity is forward, positive velocity, you're going forward. You stopped momentarily here and started going backwards until you stopped again and then started going forward again. So your total displacement, you went this distance, then you subtracted that distance because you backed up, and then you went ahead that distance. So it's the sum of these two minus that, which is what that shows. That's your displacement. The total distance traveled, though, you would have to do the area here, the positive area here, and the area here. So then it would be from this interval, which they don't tell you what it is, call it C1 to C2 or something like that, you would have to do the negative of that because you're going backwards. Okay? That gives you the positive area. So what they're showing here, these are true areas which are positive quantities. It's just this, here you're subtracting it, and here you're adding it to the others. Okay. was afraid they're going to give us an example with that. So let's do it. The velocity in feet per second of a particle moving along a line is this really squirrely looking function, okay? Where t is the time in seconds, okay? It says what is the displacement of the particle on the time interval 1 to 5. First, this is a polynomial function, continuous everywhere, smooth and continuous everywhere, okay? Doesn't guarantee it's always positive, though. But with displacement, we're not worried about that. What's the total displacement? We take the this is ds dt, right? Derivative of displacement is your velocity. Oh, this is how physicists do it, and maybe mathematicians cringe at this, so I don't know. Let's write that in differential form, dt, okay? So what you're doing now is integrating your ds. This will then give you s. The integral of ds is just s, and then do your integral dt. What would that be? Antiderivative of t cubed. T to the fourth over 4 minus 10 over 3 t cubed. Keep going well. Plus 29 over 2 t squared minus 20t, evaluated from 1 to 5. Okay? Notice that's not a 0, so don't just forget to do the second one. Calculator time. I'm not about to do that. Well, I guess I could. T to the fourth, 5 to the fourth, I think is 625, isn't it? So 625 divided by 4. I'm going to let you do it on the calculator. Minus 10 cubed times 125. I believe that's right. Plus 29 halves times 25 minus 100. That's the positive side, sort of. Okay, that'd be, so say 625 over 4 minus 10 times 125 over 3 plus 29 halves times 25 minus 100. That's the upper one, minus 1/4 plus 10/3 minus minus 29 halves plus 20. Okay. Now let's see if subtracting 1/4 from 625 fourths, that would be 624 fourths, which I think will go a whole number of times, minus, this one won't, so 1250 divided by 3. No. It's wrong. I'm getting carried away with myself here. Okay, the first one was easy. The second one is 1250 over 3 minus 10 over 3 is 1240 over 3, and that won't go an even number of times, so I'm afraid it wouldn't, sorry. And this, I'm not going to, just do it on your calculator. So I thought maybe we could do it a little easier, but we can't. So
I got 10.66.
You got what?
10.6666.
Okay. 10.66. 6666666. Okay. I think that's the same as 32/3. That's what they got in the book. Yeah, that would be 10.66. Exactly. Okay? Particle displaces itself 10 and 2/3 feet to the right. Okay? Now, what is the total distance traveled by the particle on that time interval? Oh, what a pain. Okay? Because now you have to do the absolute value of that function, which means you have to, well, here's the easy way, well, I'm not sure there's an easy way. You find the zeros of that function, and you determine when these are positive, negative, okay? And I can almost guarantee you it'll be exactly that distribution. So that means you got to find the places where it goes from plus to minus, minus to plus, because that's a nice smooth function. So the first thing I would do is find the zeros. Easier said than done. But the good news is, when t is equal to 1, notice this is 1 plus 29 is 30, and minus 10 minus 20 is 30, minus 30. So t equal 1 is a 0. Well, unfortunately, that's the one we've got right here. So that doesn't really help. At least it tells you you're starting here. Now, when t is slightly more than 1, this wins. So it starts off going negative, doesn't it? Okay? It starts at 0, but it starts going negative. So I was wrong. It's going to be negative in the first part. So now you've got to find your other zeros. Okay? And y'all remember your good old synthetic divisions, don't you? Oh yeah, I thought you did. If 1 is a 0, which we know it is, we can do that into 1 minus 10, 29, and minus 20. Oh yeah, remember that? Skip a line, draw a line. This is my way of doing it. Bring down the 1. We know this is going to come out exactly, so that's 1 times 1 is 1. That would be minus 9. This would be minus 9. That would be 20. 20 times 1 is 20. 0. We knew that was going to be a 0. But what did that do for you? It gets you to a quadratic. T squared minus 9t plus 20. Okay. Can we find our other zeros here? Well, we should. This would be t minus times a t minus. Two numbers that multiply to be 20 add to be minus 9. Oh, yuck. I thought we could. Not going to happen, is it? Think we're going to have to use good old quadratic formula, aren't we? Oh, that's right. Yeah, minus 5 and minus 4. You got it. Okay. So we have one time change there, because t equal 5 is going to be at the end, and so t equal 4. So it's going in the negative direction, if I'm doing right, for its first 4 seconds, and then going in a positive direction for its last second. So what we'll do then, doesn't seem right, but I think it is right, because by the time it goes positive, it goes really positive, okay? So let me erase a little bit of this mess. Okay. I think I can erase this with impunity. And I think I'll even move our first answer up to the top. 32/3. Wait. Okay. So the first answer is, what's it, feet. 32/3 feet, which is 10 and 2/3 feet. Okay. Was our first answer. So let's do the rest of it. I don't think I really need this either. Just remember t equal 4 is a solution. So it's going to be negative from 1 to 4. So we'll do the minus of 1 to 4, t cubed
minus 10t squared plus 29t minus 20 dt. And then we'll add to that the integral from 4 to 5 of the same thing. Okay? I just won't write all that in because I don't have room. Let's do the antiderivative. What does that give you? We just did it, so let's just use it. It will now be a minus t4 over 4 plus 10/3 t cubed minus 29, I can't write, 29 halves t squared plus 20t. We'll evaluate that from 1 to 4. And we'll do the one we did up here and just do 4 to 5. I'll be really lazy about it and do that. Okay? So let's do this one first. Pull out the calculators.
Dr. Fowler, is it negative on 1 to 4, or is it?
I'm sorry?
Is it negative on 1 to 4 or positive on 1 to 4?
Okay, that's where I was thinking. When t is a small number, let's do 2. That will be 8, and this will be a minus 40. And that will be a plus 58. So 8 and 58 are 66, I believe. Okay. Not doing as well today. And this is minus 40 and minus 20. So yeah, I think that's going to be a negative, isn't it? So I believe it's negative in the first. Am I wrong? I mean,
I don't know.
Yeah. I think your velocity is negative for the first 4 seconds and then positive only for the last second. But it's a really big positive because you got, these things evaluated at t equal 5, huge numbers minus the t equal 4, which we'll get the t equal 4 real soon if y'all do that calculation. I was surprised too. I thought it was going to be positive first and negative at the end. Well, I thought it was going to be more breaks in it, but it's not. There's only one speed change. T equal 4.
T equals 2, the function is positive.
What's that?
At t equals 2, the function.
Oh, it is positive. So you're right.
It would be 8 minus 40
It's 6.
plus 58 minus 20, which would be.
Oh yeah, yeah.
Would
Okay.
be
Okay, so it's positive first.
positive.
So turn my signs around. Plus here, minus there. Okay. Plus, minus, minus. Oops. Yeah, it didn't take. Minus, plus, minus. Okay. All right. I was thinking it had to be that way too, but yeah, if you confirm that, then yeah, it's positive to begin with for the first 4 seconds. So you do that one. Okay? And then subtract the 1, which here, if you subtracted the 1 right here, we already did that. And then the second part is the 5, which we've already done here. If you had that already, minus what you calculate here for the 4. So, sounds a little bizarre, but if you do the calculations separately, you only have to do them once. Okay? So do that for the 5. You take the opposite of that, because that's going to be the minus here. Okay, that's going to be the minus. Okay. So that, you'll take the opposite of this, the negative of that calculation. You'll calculate this at 4, do the positive of it, subtract off this one just like we subtracted it here. Then the opposite of that one, the negative of that one, plus this one again, because it's a minus. Okay, so yeah, that comes out. No, it's the opposite of that one. So, I don't have a calculator, so I can't do it. So I'm having an accountant, y'all doing the calculation. Yeah. So it's positive from 1 to 4, minus from 4 to 5. Okay. You have the same integral in both places, and so you get, and you get a minus, which gives you a plus. I don't have a calculator, so I can't do it. And the graph is shown here. I should have looked at the graph. But they come up with 71.6 feet, which would be 1, 1, and 5/6 feet. So your net was 10 2/3 feet. Your total was 11 5/6 feet. The rest is practice in doing the integral. I mean, the integral, you've done the integral once. That's the same integral every time. So it's just plugging in the 4, subtracting off the 1, just like we did there. But then negating the 5, which was there, and then adding the 4 again, because it's minus the minus, which does add the 4 again. That should be whatever you wind up with. All right. Did y'all get the answer? Anyone even try? I just don't have a calculator, so I can't punch in the numbers. So hopefully they did it right? And if indeed it did, and y'all are convinced of that, then that's the last example in section 4.4. Homework exercises will be 5 and 7, both at calcchat.com. Then any of the odds 9 to 35, they're all at CalcChat, 19's at CalcView. Either 37 or 39, they're both at CalcChat. 37's at CalcView. Any of the odds 41 to 45, they're all at CalcChat. 43's at CalcView. Any of the odds 47 to 51, they're all at CalcChat. 47's at CalcView. 53 to 57, they're all at CalcChat. 53's at CalcView. And do either 59 or 61 or both. They should both be at CalcChat. Now here's an interesting, I've never run into this one before. Buffin's, I don't even know who he was, needle experiment. If that's something of great interest to you, then by all means you can look up and see who Buffin was and write your paper on that, or what that experiment showed, or anything. 63 is at both CalcChat and CalcView. 65 is at CalcChat. 67 is at CalcChat. Any of the odds 69 to 73, they're all at CalcChat. 71's at CalcView. Boy, there's a lot of these. Any of the odds 75 to 79, they're all at CalcChat. 75's at CalcView. 81 to 83 are all at CalcChat. 87, any of the odds 87 to 91, they're all at CalcChat. Any of the odds 93 to 97, they're all at CalcChat. 93's at CalcView. And you can explore doing 99 or 101 if you would like. 103 is another one you can do. It's a CalcChat, and the other two should have been at CalcChat too. Error analysis,
I like that they put the big red X's there. Something is seriously wrong there. Figure out what the problem is. You can do 105 or 107 if you like. I'll leave that up to you. The true false, 109, you can do that. It should be at Calc Chat. 111 or 113 should be at Calc Chat. Enough. Now, do we have time to get going, maybe just barely, in... Wait a minute. Sorry, I didn't realize. Yeah, this one does have, it's in the book. Here's their answer, so we don't have to do it. Let me just do example 10 here. Definition of the displacement is just the integral. We did that, and y'all came up with 32/3. 10 2/3. Okay? So the particle moves total of 10 2/3 feet to the right. To find the distance traveled, calculate the absolute value of that. Now, to do that, the best way is to find the zeros, because at the zeros, it changes direction. And if I had looked at the graph, I'd have seen it is positive from 1 to 4 and negative from 4 to 5. Those are our three zeros. One, we can see easily, using that synthetic division, we got 4 to 5 by factoring the quotient of that. Okay? And if you do the graph, you see this is the positive, that's the negative. Duh. Okay. So what we do then is the absolute value would then be the integral from 1 to 4 of v of t minus the integral from 4 to 5 of your same v of t. Your integral is the same, okay? Your function is the same, so the integral is the same. When you do that, you'll get 10 to the, you'll get this thing from 4 to 5 minus that thing from 5 to 4. 4 to 4. This from 1 to 4, that from 4 to 5. Okay? When you go to plug, and plug in 4 here, okay, just the way it is, minus the 1 there, and that, by the way, was the same as minus 1 when you plugged it in the A part. Okay? Then you do minus this thing evaluated at 5, because of this minus sign, and then minus a minus, which is plus this thing evaluated at 4, which is the same as what you had here. So if you just be careful with this, evaluate this by itself, okay? Subtract off this with 1. Evaluate this at 4, evaluate it at 1, evaluate it at 5. You already have it evaluated at 4. Add the two 4s together, subtract off the 1 and the 5. Okay? That will work for you and be a little bit easier than trying to punch it all in several times. Because, frankly, so easy to make sign changes here. Sign errors here. Really, really easy. Okay? So be careful with them. And that gave you, they claim, these numbers. They didn't do it that way, obviously. They just did it brute force. Okay? And that gave this. Now, a good thing to do, and that's why I checked it, if you divide 6 into 71, you get almost 12 feet. Before we got just, almost 11 feet. This had better be longer. The total distance is always greater than or equal to your displacement. Never is your displacement longer than your total distance. So yeah, that worked out well. And that was the end of the slide set. Oh. All right. Now I think we probably don't have time to get into 4.5. Do you think? What's time we got? 37. We got 3 minutes. Oh, let's get started. It won't be much, but let's just at least get started. We'll just get the groundwork laid here for substitution. Frankly, I think you'll find substitution is kind of fun. We almost were doing it back when we were doing that Fundamental Theorem of Calculus Part 2. We did do a substitution there. Now we're going to do it in earnest with solving some functions. Okay, so integration by substitution. Our objectives here is use pattern recognition to find the indefinite integral. We'll use a change of variables to find the indefinite integral. That's substitution. We'll use the general power rule for integration to find the indefinite integral, which is basically going to use the same thing. Use a change of variables. I thought we just did that. To evaluate a definite integral as opposed to indefinite. Okay, we're going to do both indefinite and definite. And we'll define a definite integral involving an even or odd function. Evaluate a definite integral involving those. So let's start with pattern recognition. In this section, we'll study techniques for integrating composite functions. That's the key here. We're going to be composite functions. The discussion is split into two parts, pattern recognition and change of variables. Both techniques involve the use substitution, so why do we make this difference? With pattern recognition, you perform the substitution mentally. With the change of variables, you write the substitution steps. Frankly, I do the steps, okay? The role of substitution of integration is comparable with the role of the chain rule in differentiation. You're just doing it in reverse, okay? Now, recall that for the differentiable functions, y is some function of u, but u is a function of g, okay? U is g of x. Y is a function of u, and u is a function of x. That function is g of x. Okay. The chain rule states that the derivative of f of g of x is f prime of g of x times g prime. Good old chain rule. We did it earlier today. From the definition of an antiderivative, it follows that then the integral of a derivative of g of x times the g prime of x, that would be, if this f prime, if this is this derivative, you can do both sides, that just comes out with alpha g of x plus c. Because in other words, if the antiderivative of this is going to be that, the derivative of this will be that, and that's exactly what they told us it was. Really. Now, do I find it easy to do that way? Not particularly, okay? If you see it, yeah, do it, okay? Always remember you have to have a plus c if it's an indefinite integral, okay? We're out of time now, right? So we will pick up next time with the theorem. All right, not enough to do any new homework exercises there, so we'll see you on Monday. Now let's just get an idea. We're going to finish this section hopefully on Monday. Like I said, I think you'll find this goes pretty quickly, so it's a fairly long section. And then we're going to get started in chapter 5, okay? And I think that I'll wait and just put one test, because we're not going to do a lot in chapter 5, but we'll do a little bit. And the last test will be your final test. It'll be chapter 4, these 5 sections, and whatever we do cover in chapter 5. So I'm not going to try to do a test in 4 and then just do a couple sections in 5 and then have to do a test on that. So we'll just combine 4 and 5. That will be your test, your last test. Good deal. All right.